I mean, he could come in limping a little more or something to try to get some sympathy, maybe. Well, he just comes walking right in.
My brain's broke.
Right, yeah, see, too late now. All right, now, I was told by someone that if they were late, that they would just skip class entirely to save the bonus points. I just can't imagine. Anyway. All right, so the plan today is to take a look at some of the problems you had here. Maybe take a look at a few on page 195 if you had some questions. Talk about this implicit differentiation. Then after that, we need to take a look at the inverse trig functions, arc sine, arc cosine, what that's all about. So I am going to be kind of running through that fairly quickly today. Some of that, and we'll talk about it when we get there. Okay, but that's the plan. And after today, there's really nothing new to talk about until the gateway test next Tuesday. So it'll be about practice, practice, practice. All right, so here's number 9 right here. Now, I did pick a couple out that I wanted to talk through some things. Number 9 would be a very much like one that you would have on the gateway test. The explicit functions are ones where the y is by itself, and that's most of what the gateway test will be. Y equals a function, you do the derivative, there you go. But there'll be 1 or 2 where the x's and y's are mixed together. Now, sometimes you can get the y by itself on those, but I'm not going to give you any like that. Like number 4. There was 2 ways to do it. You could pull out the y, get the y by itself, do it that way, or you could do the implicit differentiation. But there are some where you can't do that. You have to do implicit differentiation. So the ones on the gateway test will be like that, like this one. There's no way to get y by itself here. So you have to do implicit differentiation. So we have a mixture of x's and y's. That's what we do. Couple of things we talked about yesterday that are key in doing this. First of all, if you're doing a derivative of y, you multiply by a y prime at the end. Do the normal derivative and multiply by a y prime. So e to the y, derivative is e to the y times y prime. Y cubed, the derivative is 3y squared, y prime. Right? But if you do x cubed, the derivative is just 3x squared. We don't tack on an x prime. Why? Because x prime would be the derivative of x with respect to x. That's just 1. But we tack on a y prime because the derivative of y with respect to x is dy over dx, or y prime. Okay? So it's what it's with respect to that is the key. All right, so that's one thing. Do the normal derivative, tack on a y prime. Now, the second part of that is you have to get the y prime by itself. And, well, no, I take that back. The other thing you really have to watch for on doing these is when you have an x times a y, when you have x's and y's multiplied together, you have to do the product rule. Actually, if you had x's and y's divided, you'd have to do the quotient rule. We haven't run into any of those, but if you had one of those, you'd have to do that. I don't anticipate we're going to run into any of those either. But, and that's the mistake I had several people already today make on one like number 9. That's why I wanted you to do this one, is that has to be a product rule right there. And I would take the negative, I'd put a 1 there, and I would take that negative and attach it to that x. You don't have to put a 1 there, but that negative is attached to that x. That way you don't have to worry about distributing it through. So, derivative of x squared, 2x. Derivative of this is the product rule. So derivative of the first, derivative of negative x would be negative 1 times y left alone. Then the negative x left alone times the derivative of y. Derivative of y is y prime. Then the derivative of y squared is 2y, y prime. Now, some people, again, have been asking me, like on 3y, why isn't the derivative 3y, y prime? Well, think about it. What's the derivative of 3x? 3. The derivative of 3y? 3. And then tack on the y prime. So the derivative of 3y is just 3y prime. The derivative of y there is just y prime. Okay? All right, and the derivative of 1 is 0. Now we need to get these two together. So we'll leave those there. We'll move those other ones over. We'll take out a y prime, which we can always do in these problems, and then we'll divide. Now, it does occur to me here, and I think some of you may have done this, it depends which side you get the y primes on. If you decide to move your y primes over to that side, then your signs are going to be different than mine. So you might get this here. But that's just opposite the top is opposite, the bottom's opposite. If you have opposite divide by opposite, it's the same. It's kind of like getting 3 over 4 compared to negative 3 over negative 4. They're the same thing. The negatives cancel. So I can pull a negative out of both of those, cancel them, and get this. So when you do it, I will be aware that either one of those answers would be okay. All right, depending on which side you get the y primes on. Okay, they are equivalent. All right, let's talk about number 21. Well, now, number 10. Then number 10 said, and there was 2 problems you had to do on number 9, right? I just did one of them. And I wanted to do the one with the negative because you got to make sure and carry that through. But number 10 then said, which equation goes with which graph? And they gave you a hint. They said, put in 0, 1, or pick a point and plug it in because they have different slopes at different points. So if you go to 0, 1, one of those ellipses looks like this, the other ellipse looks like this, and here's the point 0, 1 right there. Well, one of those has a negative slope and one has a positive slope. So let's put 0, 1 into this one. If I put a 0 there, that's 0, that'd be 1. Put a 0 there, and that'd be 2. And so I get 1 over 2, which is 1/2. That's got to be the positive one. So this one's got to go with the ellipse that's going up and to the right. The other one must go with the other one. You better get a negative on the other. Okay? All right, number 21. Now, I don't want, we probably won't spend enough time for you to write all this down. It's up to you, but it just, this one just had a lot of algebra. I don't anticipate you having to do this on the gateway test unless this was one of the harder ones. You know, in other words, we said on the gateway test you'd have, 10 problems, maybe 3 a little easier, maybe 4 kind of in the middle somewhere, 3 a little harder. If you're going to get 8 out of 10, you're going to have to be able to do at least one pretty hard one, I would think. Kind of divided up that way. Now, depends which ones you think's hard. Some of you will think they're all easy, and some of you might think they're all hard. I don't know, but that's kind of the idea, right? So this would definitely be one of the harder ones, just because of all the algebra and the simplifying to do. Quite honestly, I'll probably save the harder ones more for the other ones that we're working more on, the quotient rules and the product rules and those kind of. Okay. So I wouldn't anticipate you having to go through all this. One like number 9 would be more like the type I'm talking about with the implicit differentiation. So anyway, in this one, you're going to bring the 2 down in front. You get this, leave the inside alone, times by the derivative of the inside, 2x plus 2y, y prime. Now, I did become aware, talking to a few people this morning, some of you are putting, like when you tack on your y prime, you're putting a dot, a times y prime, which is okay, but then it's confusing you as you go to move things around. It's just 2y, y prime. It's just one term. It just moves together. So some people, when they put that dot in between there, it tends to then confuse them. So don't do it, okay? Don't do it. So here we got to do a product rule. I would put the 25 with the x, keep the y separate. So the derivative of 25x is 25. Put the y left alone. 25x left alone. Derivative of y is y prime. So don't forget the product rule. Whenever you have x's and y's multiplied together, you've got to do product rule. Now, where you go from here is interesting. What I was going to suggest and what I worked out here is I multiplied the 4 through there, okay, and made that 4x squared and 4y squared like that, okay? Now, my plan at this point was to FOIL this out. That's what I did here. Because you've got to get the y primes together, and there's no way to extract this y prime from inside these parentheses without foiling it out and getting a bunch of terms there. Now, what somebody came in this morning and what they did, which actually works just fine, they took this parenthesis and just treated it as a single quantity, and they took this parenthesis times 2x and wrote that down, and didn't write it out. They just wrote parentheses times 2x and just left it and didn't distribute it, which is fine. So they took this times 2x and then took this times 2y, y prime, and then that second one had the y prime in it, and they moved that over and just kind of left it, and that saved them a little bit of algebra, which is okay. You could do that. But what I did is I went ahead and just FOILed the whole darn thing out. So 4x squared times 2x is 8x cubed, and 4x squared times 2y, y prime is 8x squared y, y prime, and blah, 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 blah. I don't know. So I end up with 4 terms. When I FOIL it over here, I get that. So now I got 3 terms in blue here that all have y primes in it. So I've got to get those together. But I first needed to FOIL it so I could get everything all written out in different terms. So I'll leave those 2 there. I'll bring the 25xy prime over. So they're all 3 over here. These without y primes are all over here. Then I'll factor out a y prime, which I didn't show, but we'll factor out a y prime, so that'll leave you these three things in blue, and then I'll divide those over, and that's what we end up with, is this kind of mess of a thing right here. Now, I don't, and that's what we would have to be able to do for a gateway problem. But again, I don't anticipate there being one with this much algebra on it, right? The harder ones I'd say for some other stuff. But that's what we would be after, to find y prime. Now, in this particular problem, the directions were a little different. I don't even know if you read the directions, but the directions said find the equation of the tangent line at the point 1, 2. Right? So what we need is a slope, right? Whenever we write the equation of the tangent line, we need a point and a slope. They gave us a point, so what we need is a slope, which is what y prime is a slope. Well, did I need to go all the way down to here to find y prime? What could I have done? Way up here, right? Way up here, I could have put a 1 in for x, all the x's. I could have put a 2 in for all the y's, and all I'd have been left with were the y primes, right? And so I could have put a 1 and a 2 in up here, found y prime at that point. And that's probably what I would have done if that was the prime. If this was a test and the problem said find the equation of the tangent line, I probably just would have went to here and then plugged my 1 and my 2. Okay? But for us in the gateway test, the question is find y prime. So you want to get to here and then you'd be done. Anyway, I went ahead and I plugged in those numbers. I got 2 11s. So my tangent line is 2 11ths, and then x minus 1, and then plus 2. Right? The equation of the tangent line is that thing there in red. Okay? So that's what they were asked for in that problem. All right, same thing with 22. Actually, same thing on 19 and 20. But it's good practice to go through and be able to do that. But again, this one's a little extensive. We're not going to have to do that much algebra on our implicit differentiations usually. Okay? All right, so page 195. Any that you try now, we're not going to take a lot of time to do a bunch. Tomorrow and Monday will be a lot of that time. We'll be working on those. But did you come across some? Look like a lot of you just started with the first 10 or so, which is fine. And you can also mix, and match and just whatever. Yeah, Kel? 16. Read it to me. All of the whole thing?
Yeah. Like, instead of
I get it.
and it was the square root of the side of
So it was the square, so the 1 was outside of everything? You know what I should do? I should just say.
Okay.
What?
It was the square root of 1 plus 2.
There you go. All right. I got it. So the whole thing is, I've got it right here. 1 plus t cubed. I put the parentheses around the t cubed, and then cosine of t. And then all of that to the 1. Okay, there we go. So, now first of all, if I was doing Leibniz notation when I do this derivative, what derivative am I about to do here? dg dt, right? We talk about dy dx and right that kind of stuff. I'm about to do dg dt, the derivative of g with respect to t. We would usually just write it g prime, right? All right. Anyway, and if you want to, when you're doing these, you can change all the input variables to x's. They did do that, right? Some are u's and w's and z's and whatever. Were there any that had y's? I'm curious. Because there could have been. I mean, if I gave you the function h of y, and then they all had y's in them, when you did those derivatives, would you put y primes on? You wouldn't put y primes on, right? Because you're doing the derivative with respect to y. And so if you do the derivative with respect to y, then the derivative of a y would be dy over dy, which is just 1. See the difference? So when we're doing implicit differentiation, we're tacking on these y primes. It's because we're doing it with respect to x. That's why we need the y prime. All right, it's all about what the input variable is. Anyway, so we start on the outside. We bring the 1/2 down in front. We get 1 plus t cubed cosine t because we leave the inside alone, right, to the negative 1/2 times, oh God, start over. All right. I can see what's happening. Start way over here. All right. G prime of t equals, okay, bring down the 1/2. 1 plus t cubed cosine t to the negative 1/2 times the derivative of the inside. Now, so like I've been telling you before, when I do these problems like this that have an inside, and especially a somewhat messy inside, then I'm going to do this. I'm going to put a big set of parentheses. Who knows how big, but kind of you start to learn about how big you need. But the reason I do that is because I know what I'm about to do now. And sometimes, like we talked about getting lost in the weeds, right? You're so into all this stuff, you kind of forget where you were in the big picture of the problem. I know what I'm about to do now. All is going to have to be inside one set of parentheses because I have to do the outside, leave the inside alone, times the derivative inside. And when I get caught up doing the derivative inside, I want to make sure it's in the right place. Okay, so now what I'm doing is just the blue. All I care about is this part right here now. And that's going to go in here. So derivative of 1, 0. So good, I can ignore that with the plus. So now I'm caring about is that, and that's a product rule. So the derivative of t cubed is 3t squared. Leave the cosine alone. Plus, well, it will end up being minus, right? Because I'm going to do t cubed left alone times the derivative of cosine, which is negative sine. And again, whenever you get that negative sign, I've talked about this, whenever you do the derivative of cosine, it's a negative sign. If I put the negative there, it looks like a minus. So I want to bring that around in front so I don't make that mistake. So it's a negative or the plus, return to minus, whatever. Okay? Now, the next step is to literally step back and look at it and say, is there anything I can simplify, anything I can put together, maybe cancel, whatever. A couple things you have to be careful of with the algebra. First of all, if you've got plus signs, like we do here, that's got to stay together, that's got to be grouped. That's where you're thinking about factoring stuff out. Second thing to be wary of, anytime you have a power outside of parentheses, be careful with that. You can't be pulling things out of there or putting things into there when there's a power around some parentheses. So, when I look at this, I think, is there anything I could do with this? Anything I can put together? I don't think so. Now, could I take out a t squared out of this group? Sure, I could take out a t squared. I could bring that around front, but it doesn't redo anything for me. Factoring to me is usually if you can pull something out and then cancel it with something on the bottom or something, that would be good. But to me, it doesn't look like I can do that. So for me, I'm done. I think you're done then. Okay? So like we were saying, on a lot of these, you get, you do your rule, you write it out, and you're pretty much done. There might be a little bit to do, but maybe not a lot to do. And maybe not anything. Yes?
We do 7.
Number 7. I hope that's not the one I think it is. Oh, that one's. Oh, yeah, that one's. Oh, no. I thought you were going to say 8. Okay, 7. Did anybody try 8? You're going to ask about 8? Okay, we'll do 7, then we'll do 8, and then that's it for today. All right. So 7 says W. I'm just going to call it Y right now. It doesn't really matter. E to the U squared. Now, this is important. I don't like how they didn't put a parentheses there. That's the default. But that's different than this, right? It's different than e to the u and then squared. Because what's e to the u and then squared? That's e to the 2u, right? Power on a power, you multiply the powers. So that is not what this one is. It's this right here. They didn't put parentheses there, but they should have. Okay, it's kind of like writing sine x and not putting the parentheses around the x. All right? So we have e to the u squared, and then, now I lost it, times tangent of, and then that would be u to the 1/3, right? Cube root is 1/3, right? Now, I've seen people making the mistake whenever they see a square root or a cube root, they're putting a negative on it. Remember, negative is top, bottom, flipping, right? Not root. Okay, so the bottom number is the root in the fraction, so it's u to the 1/3. Okay, this is a what kind of rule here? So first it's product rule. Now it's chain rule in there, but it's really a product rule to start, right? Because we got two things multiplied. So the product rule says do the derivative of the first. So we got e to the u squared. So e to some stuff. The derivative is e to that stuff times the derivative of that stuff, the inside. So it'd be times 2u. And then it'd be times the tangent left alone. Right? Remember, product rule. Derivative of the first part, second part left alone. Now, another thing I said, you got to be wary in algebra of the plus signs because you're going to have to group those. Right now, I don't have any plus signs in here, so I don't have to worry about it. It's like A times B times C, right? And so I don't really have to worry about parentheses around stuff. I do around kind of my arguments, but that's about it. Plus, now we leave the first part alone, e to the u squared, and we do the derivative of the second part. Derivative of tangent of some stuff is what? Secant squared of that stuff times the derivative of the stuff inside. Derivative of u to the 1/3, which would be 1/3 u to the negative 2/3. Right? I ran out of room again. Okay? And that's it. Now, you step back, you say, can I put anything together? So what you have is two terms. You have one big term here plus one big term here, right? So can I put anything together inside those terms? Well, not really. I could bring the 2 around front. We're kind of used to seeing the 2. That's kind of weird having it stuck in the middle. So we're used to the 2 being around front. Even the u could probably come around front, but that's just rearranging. So I don't care. Okay, over here, the 1/3, u negative 2/3, maybe that could come out in front, but again, it's rearranging. There's nothing I could do there. They both have an e to the u squared. I could pull that out, factor it out, but it doesn't cancel with anything, so I wouldn't do that either. Okay, so I think you're done on that one. You could literally leave it just like that and be fine. Okay, now if there would have been a 6 on this e out here, that 6 and that 1/3, we needed to multiply those together and make a 2 or whatever. But since there isn't, we won't worry about it. All right, let's look at number 8. Number 8 says y equals x to the 2/3. We did this one last period. And it turned out to be kind of good. Over ln x plus e to the x cosine 4x. So this would definitely be a hard one, just the amount of stuff that's in it. And there is a little bit of simplifying in here that is hard to see. Okay? So it would be in the tough range, which is why you're allowed to miss 2 and still pass. All right. So we're going to start. It's a quotient rule, right? There's a product down here, but we'll worry about that when we have to. It's a quotient rule to start. So the derivative at the top. Now there's that plus sign, so we got to worry about those plus signs. So we got to keep that together. So we need parentheses. So that top's got to stay together. So it's 2/3 x to the negative 1/3 plus the derivative of ln x 1 over x. Okay, so that's got to go together. That's got to have parentheses around it. There's just no way you can do this without parentheses around it. Times the bottom left alone. Now that doesn't have plus signs in it, so I wouldn't have to put parentheses around that. But I could. Okay? So I got a dot there. I could have a dot there too. I don't need the dot either place, but don't let that throw you off. Okay, so I got that. Now minus. The top left alone has to be in parentheses. Times the derivative, oh shoot, I'm out of room, but that's okay. We'll make it work. Derivative of the bottom. What do you got to do for the derivative of the bottom? Product rule. So I've got the top left alone, and now I have to do the derivative of the bottom. So we'll make it work. So the derivative of the bottom is going to go right there. So the derivative of the bottom is product rule. So we have to do the first, right? So e to the x derivative times cosine 4x left alone plus, plus the e to the x left alone times the derivative of cosine 4x. What's that? Negative. So I better put the negative out here, and I'm going to put the 4 out there too. And then the cosine, oh yeah, sine. Then when I start writing upside down, all right, sine 4x. right? All over e to the x cosine 4x squared. And I would never try to square that bottom and FOIL it. It usually never works. The only thing you might do is write it as e to the x cosine 4x. Sometimes this is helpful. Times e to the x cosine 4x, because that's what that means. That means you got two of them, right? You got two of them down there, right? So that might be one way you could write it. So you could write it as squared, or you can write it out like that, whatever. All right, now. Okay, so that's hard enough just to get to that point, but really it's pretty fundamental with all the different rules we have, right, that we have to do. Now, is there anything we can simplify? A what? Not quite. You're on the right track. Okay, so when you do a quotient rule, you got u prime v minus uv prime. So you got two pieces up here where you can factor something. So here, this has an e to the x. I mean, this is different than this, so we can't do anything with that. We have e to the x, we have a cosine 4x. I see one there, but it's not a factor, is it? That e to the x cosine's in here with the plus sign. But what could I take out? The e to the x I could, not the cosine, because there's not a cosine here, right? So in this set of parentheses, I could take out an e to the x, right? So I got this thing, and I got this thing, and in this thing I could take out an e to the x. And so I'd have an e to the x as a factor in this thing, and I have an e to the x as a factor in this thing, which I could then pull out of there, right? And that's the only thing. But I could take that e to the x out, so that e to the x would end up, that one would be gone, it would be ended up coming out here, right? And this e to the x and that e to the x would be gone, because I could pull those out, and then pull it out of here, right? And then this e to the x would cancel with one of the e to the x's down here. So that's a lot of work for very little gain, but it was a little bit of gain. And so my bottom would end up like this. It'd be an e to the x and a cosine squared, and the e to the x would be gone from up top. And yeah, on the gateway test, if that was on there, if that was one of the more difficult ones, you would have to do that. Okay? If you get to the 7th gateway test, and you get that first part, I'd probably give it to you. But you don't want to get to the 7th. Okay? I might be a little more lenient on that if you could do all the rest of that, because in the end, it's not about algebra. But if you're going to get a 30 out of 30, you're going to earn that part of it, right? If you want a 30 out of 30, pass it the first time, you might have to do something like that, right? But that could be one of the two you miss, too, and still pass. So that would be on the hard end, for sure. Quite nasty? Maybe. Right? All right. So let's talk about, let's move on now. Tomorrow and Monday is going to be a lot of this kind of stuff. I'll spend some time during the block working some out for you, talking about the different things, but a lot of the time is going to be you getting to work and practice and work together and check and that kind of thing. Maybe we'll spend some time with me giving you some, just like a little practice test. Maybe I'll give you 1 or 2 or 3, let you do it, then we'll check them. Maybe that would be good review as well. Okay? So we'll see. All right, so get your notes out. Now, I would say, as you're doing that, you do not need to feel inclined to write down all of the stuff that we're about to go through. Matter of fact, I would probably write down very little of what you see on the screen right now. I will try to tell you when we hit a couple of important things you might want to jot down. We're going to zip through this to the point where I think you'd be better off just trying to soak in a little bit of what we're saying rather than try to copy everything down. Because what I want to do, we're talking about inverse functions, right? What we want to end up with in the next 30 minutes is we want to end up with the derivative of arc sine of x. We want a rule for the derivative of the arc sine of x. Now, it's on that derivative sheet, and I'm guessing you'd be perfectly happy if I just gave it to you and told you to use it, right? And don't even care where it comes from. I understand. But I would not be happy. So, I got to earn my money. But it is worthwhile for us to review some of the ideas about inverse functions, because that will come up from time to time as we go throughout the year. Short term, gateway test next week, all you really need to know is the rule we come up with at the end. Okay? For the long term, we need to review some things about inverse functions. All right. So I've put two different types of inverse functions up here that are pretty famous ones: x squared, square root of x, and e to the x and ln x. They're inverse functions. They kind of undo each other. Inverse does not mean reciprocal, right? Okay? These are inverse functions. Kind of like inverse operations in algebra. Addition and subtraction are inverse operations. Multiplication and division are inverse operations. They kind of undo each other. All right. So if we take a function y equals x squared, here's a graph of it. Hopefully you remember from last year that inverse functions, we interchange the x and the y. Does that sound familiar? We interchange the x and the y. And so if I take y equals x squared and I interchange the x and the y, I get x equals y squared. And then if I solve for y, I get plus or minus square root of x. That's why those are inverses of each other. When I interchange the x and y, those are the functions I get. And if I look at the graph of plus or minus x squared of x, I get this. Now it's not a function. It fails the vertical line test. So usually when we talk about the square root function, we only talk about the positive part of it, which would be this part, the top half. Okay? So what that points out, and that's going to be a recurring theme here, is that when you do inverse functions, sometimes you have some domain issues. You have to restrict the function and so forth so that the inverse actually is a function. Because another thing you might remember about inverse functions is their graphs are kind of a mirror image. If you drew a diagonal line right through here, the inverse is a mirror image in that line y equals x right through here. And anytime you have a function that fails the horizontal line test, that is, if I have a function like this parabola and a horizontal line cuts through here, when I look at its mirror image, it's going to fail the vertical line test. Okay? So we may have to restrict the domain so that the other one will be a function. And so that's going to come up with the sine function here a little later. Now with e to the x, it doesn't matter. If we take y equals e to the x, we interchange the x and the y. Then we solve for y, so we do the log of both sides. We get ln e to the y, we bring down the y, ln e is 1, so we get y equals ln x. So that's why those are inverses of one another. We look at their graphs, we can tell they're kind of mirror images. Right? Here you'd have this, the mirror would go right through there, and then you'd have that over there. Okay? Matter of fact, it'd probably be easier to see if we put that on. Okay, so you can kind of see that they're mirror images. Okay? All right, so that's some basic ideas about inverse functions. All right, so if we have this, I wouldn't write this down either, but so what we learn about inverse functions then is they undo each other. So if we take x and we put it into the e function, and then we put that into the ln function, we get back what we started with. We know that's true. Bring the x down in front, ln e, yeah, that works. And the same thing here. Now, there are some issues though. Domain kinds of issues. And again, we just got to kind of be aware of it. And we can have the calculator check this out for us. So if I put in ln e to the x, calculator says that's x. Okay, no problem. If I do it the other way, if I go e to the ln x, I get this warning. And the warning is the domain of the result might be larger than the domain of the input. Now what do they mean? Well, what they mean is, if I put it in this way, let's think about what x could be. What's the domain here? What can I put in for x and then put it into the e? Anything. E to the positive, e to the negative, I can put anything. E to the 0, I can put in anything. Okay? What about here? What can I put into the ln function? It can't be negative, right? Here's the ln function. We only put in positive values. You can't put a negative into the ln function. So, we only can put positives in here, which means we're only going to get positives out, right? But normally x could be anything. So if you just say that it's x, right? So that's what it says. The domain of the result might be larger than the domain of the other one. So x, just by itself, you say, well, x can be anything. Well, it can't be in this problem. It'll only be positive, okay? Because of the way we started. So all that means is that when you're doing inverses and you're putting one function inside of its inverse, they should just cancel each other out. And you get back what you started with. But you have to understand that there might be some issues with the domain. We're going to see that when we get to the sine function as well. Look at square root. Let's do the same thing here. Now, what about this one? When you put in square root of x and square it, you should just get x. But what is my domain here? What can I put in here for x? Only positives. Unless we were doing i's, imaginary numbers, but we're not. So, when I go to the calculator, I'll probably get that same warning, right? So if I do square root of x squared, I get x, but there's still this warning, which is saying basically that, hey, you can't get any old x out here. You're only going to get positive x's out because the original has a domain that's just positive. So that's what that warning is. Okay, now let's go to the next, the other version. If we go the other way, what about this way? What could x be here? Anything. Then we square it, and then we do the square root. So that shouldn't be a problem. We should just get x. But then you say, well, wait a minute. What if I put a negative 3? If it can be anything, let's put a negative 3 in for x and square it. What do you get? 9. What's the square root of 9? Well, careful, careful. It's 3, right? Remember when do we do plus or minus? When we're doing an equation, we're square rooting both sides. That's when we do plus or minus. When I just ask you what's the square root of 9, it's 3. So think about what we just said then. If we put in a negative 3 to start, this inverse thing says we should get back what we started with. But if I put a negative 3 in the start, I square it, I get 9. Square root of 9 is 3. I don't get back what I started with. I get the positive version of what I started with. Well, the calculator does take care of that for us. If we tell the calculator to do square root of x squared, it gives us that. Because it's saying, yeah, you can get anything out, you can put anything in for x, but you're only going to get out positives. Okay? So again, I only show you this to just make you aware that inverse functions should cancel each other out, but there might be some domain issues that have to be dealt with. All right. Now, moving on. We're working our way slowly but surely into the derivative of the inverse sine function. Okay, so let's talk about sine. Now this you might want to write down. This might be worth writing down here. So if we take the y equals sine of x function, okay, I've tried to write some things we know about the sine of x function. Now, what I didn't write down is, it's positive in the first two quadrants, negative in the third and fourth quadrants, that kind of thing. But the sine function, now we've got to talk about the x and the y, the input and the output. Because remember, with inverse functions, we're interchanging the x and the y. We're interchanging the inputs and the outputs. So this becomes important. So in the normal sine function, we put in angles like pi 6 and pi fourths and pi and those kind of things. Now, those are just numbers. I mean, pi is just 3.14. So we could do the sine of 2, It just wouldn't be any number we memorize. So we usually work with pi 6 and those kind of things. But we're thinking of angles. We're thinking of rotations around the unit circle. The output we get is just numbers from -1 to 1. So when we do the sine function, the outputs are numbers from -1 to 1. The inputs, though, could be any number. And we usually think of them as angles. All right. And I drew a picture of the sine graph. Now, if we interchange the x and the y, we get x equals sine y, and now we want to solve for y, like we were doing on those other problems. So if we solve for y, we have to get rid of the sine. Now you can't divide because that's not times, okay? I know we want to think that's sine times y. It's not sine times, it's sine of y. It's a function. We've got to undo sine. Well, that's the inverse function. The arc sine. Now, unfortunately, somewhere, some dummy decided to call arc sine sine -1. Now, that's horrible notation. I can't believe it's hung on this long because it does not mean reciprocal. -1 power usually means reciprocal. Well, if this was reciprocal, that would be cosecant. That's not what it is. Inverse sine is not cosecant. Okay, the reciprocal of the sine function is cosecant. the cosecant function, but that's not what this means. I hate that notation. You'll never see me use it. That's why we'll call it arc sine. Okay? It's the inverse sine function. Now your calculator uses the sine -1 function. That's fine. We just got to know that that doesn't mean reciprocal. It means the inverse sine function. Okay, but now look what you get then. So now you got y by itself, but now keep in mind what's what here. The y are angles. Remember when we interchanged our x and our y, now we switched the x and the y. So now instead of the x being angles, the y is now angles. So our output of the arc sine is pi sixths and pi fourths and those kind of things. The input of arc sine are the values from -1 to 1. Okay? Keep in mind that when we do the inverse function, we interchange the x and y. So if I ask you on the homework, what's arc sine of 2? They might ask that. There are some questions about that in the homework. What's arc sine of 2? What do you say? What's the arc sine of 2? Does not exist. It's undefined. Why? Because right here, arc sine, the input into arc sine has to be values between -1 and 1. That would be the same question if I ask you this. Where does sine x equal 2? It doesn't. Sine x doesn't ever equal 2. If you do the arc sine of both sides, you get x equals arc sine 2. It doesn't exist. Arc sine of 2 doesn't exist. The numbers that you put into arc sine have to be the same as the outputs you would get out from sine. Okay? Keep that in mind, because that's what you do with inverses. You interchange the x and the y. All right. These are just this is stuff you did last year in trig, but it's usually pretty shaky. All right. So that's the arc sine function. Now, if we graph the arc sine function, and actually on our calculator, let me show you both of those situations. Let me type in, you can actually type in arc sine. I type in arc sine of 2, I get this big error message, right? Non-real result. You can't do arc sine of 2. All right? But now look what the calculator does. It goes back to this notation. That's fine. It's under the trig button here. The inverse trig functions are down here. Okay? All right. Now, I've got a graph up here. Here's a graph of the arc sine function. And notice it actually just stops right there. And that's because of those domain issues we talked about. It's kind of like the parabola, where when we do the inverse of x squared, the parabola, we only get the top half of the parabola. Otherwise, it won't be a function. Because think about what would happen if we did the mirror image of this graph here. We would get this graph that snakes along the y-axis. Well, it would fail the vertical line test. So what we do is we just take this piece of it from here to here, and we do the inverse of that, the mirror image of that. So what do we get? We get x values that go from -1 to 1. Remember, our x values, our inputs are -1 to 1, and our outputs are between -pi halves and pi halves. Now that would be in the the first and the fourth quadrants. -pi halves to pi halves is the first and fourth quadrant. Sine's positive in the first quadrant, and it's negative in the fourth quadrant. That'll take care of all the sine values. Okay? Now, what would a problem that you would have to do look like? This is an old trig problem, so you might jot this down. So what is arc sine of 1/2? Now this should be something, in the first part of your homework they're going to ask you some of these, so it's good trig review. Anybody? What's arc sine of 1/2? I believe it is pi 6, right? And I didn't give you a lot of time to think about that. You know, you'd have to picture your unit circle, draw it out, sketch it out, whatever. But I believe it's pi 6. But that's what that is. Now think about this. That's the same question as asking, when does sine of x equal, when does sine of x equal 1/2? That's what that's asking, right? Well, that's pi 6. It's the same thing. But the problem is, does sine equal 1/2 only at pi 6? When else? Plus 2 pi, which would be like at 13 pi 6, and on and on. And there's another place. What about the second quadrant? 5 pi over 6, right? There's a whole bunch of times. So if we were solving this equation, we'd have a whole bunch of solutions. But we're doing a function, and remember, a function, one input can only have one output. So we can only get one answer out of this. So I'm curious, what does the calculator say? So if I go into the calculator and I type in arcsine of 1/2, it gives me pi 6. It doesn't give me any of those other ones. Well, that's because it's restricted from negative pi halves to pi halves. What if I put in negative 1/2? Where does sine equal negative 1/2? 7 pi 6, 11 pi 6, but didn't we just say it was going to restrict from negative pi halves to pi halves, which is the first and fourth quadrants? So which answer do you think we're going to get? 11 pi 6? Is that 11 pi 6? It's the same thing, it's the same angle, but it's a different value though, right? So we would, because it's going to use between negative pi halves and pi halves. So it can't use 11 pi 6 because that's not between negative pi halves and pi halves, right? It's first and fourth quadrants, but we would use the negative version in the bottom quadrant, and we use the positive version there. Okay, but those are just some of the little tricky things. We're not going to spend a ton of time dealing with, that. But I mean, it's good trig review and thinking about those things. But what I want to point out to you is this points out this idea of the restricted inverse function, right? When we looked at this graph here a minute ago, that it's only going to give us these values in there where that graph is. Okay? All right. So we're getting there. We're getting closer. All right. So then in trig class you had problems like this. What's the arcsine of 3/5? Well, that's no value we know like 1/2 is. So what you had to do in a problem like that is you had to draw a triangle. You said, okay, what angle would have a sine of 3/5? Remember old SOHCAHTOA, opposite over adjacent, right? Or hypotenuse, excuse me. And the Pythagorean theorem would tell us what's this? 4, right? But that doesn't really help me. I still don't know what angle that is. But we could draw a triangle. Actually, so what you ended up doing was a problem like this. So what the actual problem you used to do in trig class was this problem. What's the cosine of the arcsine of 3/5? So what you would do is you would draw your triangle. You'd say, okay, the inside part is the angle that has a sine of 3/5, which would be this angle here. And then what's the cosine of that angle? 4/5. So those are the problems you used to do in trig last year. Okay? So the cosine of the arcsine kind of thing. All right, now that brings up the idea that, okay, so we can put an inverse trig function into another trig function. That's kind of like putting a square into a square root or an e to the x into an ln. All right? So let's investigate that a little bit. We're getting close. So what about this? What if we did then put a sine inside of the arcsine? They should do what? Cancel each other out. They're inverse functions. So this answer ought to be pi 6. So let's let the calculator check that out for us. Arcsine of sine of pi 6, and sure enough, it's pi 6. But what if we change that to 5 pi 6? What's the sine of 5 pi 6? Wait, go back to this. What's the sine of pi 6? 1/2. What's the arcsine of 1/2? Pi 6. We just got to talk about that. What's the sine of 5 pi 6? 1/2. What's the arcsine of 1/2? Pi 6, not 5 pi 6. Once again, this brings up this idea of the domain restriction. We think it should just cancel itself out, but because of the domain restriction, that's something we have to think about. Okay, so we're almost there. Thank you for your patient attention. Now, I would not write any of this down. Okay? We'll have a result from this here in a second. So now we've talked about all this. We've worked our way all the way to the inverse trig function. Okay? Now let's talk about what we really care about, which is derivatives of inverse. So I went back to my simple example, square root and x squared. I got an x squared parabola. There's a point on it, 3, 9. Here's the square root. Sideways parabola has a point 9, 3. Of course, we interchange the x and y, so that's not surprising. Okay? Now let's do the derivative. So I do the derivative of this, I get 2x. I want to plug in the slope at that point, so I plug in a 3. I get the slope of 6. Seems reasonable, be pretty steep. Slope of 6. I'm going to take my square root, which would be x to the 1/2. I'm going to do my derivative, which is this. I'm going to take that negative power, flip it to the bottom. 1/2 power be a square root. My derivative would be this. Now I want to do the derivative at its corresponding point. Its partner, if you will. 3, 9 is kind of a partner point with 9, 3. Problem is I can't plug a 3 into this for x. I got to plug what? A 9. I plug the 9 in, square 9 is 3, 3 times 2 is 6, I get the slope of 1/6. Makes sense, not very steep. Is it a coincidence, 6 and 1/6? No. The reciprocal. So here's what you could write down. The derivative of inverses, is the reciprocal at the interchanged points. Now, hopefully a month from now, when we read that, that'll make sense. But I'm not guaranteed. Okay? The inverse functions have reciprocal derivatives, reciprocal slopes, but not at the same point. It's not this one's at 3 and this one's at 3. On this one's at 3, this one it's at 9 because we've interchanged the x and y. So that's why I say that they're interchanged points. Okay? Now that's something we'll come back to a lot later. That's more long-term, big picture kind of stuff. Okay? All right, because it has to do with inverses and interchange the x, y, and slopes and so forth. Okay, so there's a nice example. All right, finally, here we go. We're going to do this. Don't write this down. So, we want to do the derivative of arc sine. So I'm going to start with this. Everybody agree with this? Sine of arc sine of x equals x? They undo each other. You say, wait a minute, we were just talking about how they didn't undo each other. No, that was in this case. Let's see, this case they did. In this case, it was a problem. If we had the arc sine on the outside, then we had a problem. But if we have the sine on the outside, we're okay. Okay, so we have the sine on the outside, we're good. All right, so sine of arc sine of x is x. Because they're inverses, they cancel each other out. Now what we want to do is a derivative of both sides. Okay, do the derivative of both sides. Well, this is a chain rule, right? So, do the derivative of the outside. Derivative of sine is cosine, leave the arc sine alone, times the derivative of the inside, derivative of arc sine. We don't know what that is. That's what we're trying to figure out. So I'm just going to write arc sine prime. Right? It's a derivative of the inside, so it's a derivative of arc sine. And the derivative of x is 1. Right? Okay. Now I'm going to take this, I'm going to divide it to the other side. So what I got? The derivative of arc sine, which is what I'm looking for. The derivative of arc sine is 1 over the cosine of arc sine x. Don't write that down. That's not our rule yet, but we're almost there. So the derivative of arc sine is that. All right. Oh, shoot. Don't look. Close your eyes. Quick. Close your eyes. Dang. God, darn it. You're looking. You all get your eyes open. Yeah. That's a lot. All right. Dang. All right. Merry Christmas. All right. So, the derivative of arc sine is 1 over cosine arc sine. Some of you are going, oh, I didn't know what he was doing. I get it. I mean, this is pretty fast. A lot of stuff I'm throwing at you. But right here at the end, we want to do cosine of the arc sine of x. Well, that is exactly what we were doing right here. Cosine of the arc sine of x is what we want to do right now. Well, we were doing cosine of the arc sine of 3/5, right? So we said, so the inside is what angle would have a sine that's 3/5, right? What angle would have a sine that's 3/5? So we drew a triangle where the sine was 3/5, 3 over 5. So this problem is, what angle would have a sine of x, right? So it would be x over 1, right? That's the angle that would have a sine of x. Now, we want to do the cosine of that, which means we need this over 1. Well, what would this be? Well, it'd be Pythagorean theorem, right? Pythagorean theorem. German short hair, well, this is German short hair. So it'd be German short hair, I'm running out of time, squared plus x squared equals 1. So German short hair squared would be 1 minus x squared, and then it would be the square root of that, right? So this would be the square root of 1 minus x squared, right? So that's the triangle that would have arc sine of x. So therefore, the cosine of that would be this over 1, which is just this, right? So the bottom is just that. So there is the derivative. I made it. 4 minutes to spare. The derivative of arc sine is that right there. I know you'd have been perfectly fine with me just giving it to you and forgetting all the rest of this. But all this stuff we went through about inverse trig and the inverse functionality connect is something worthwhile to talk about. Even though you probably wouldn't want to be tested on that right now. You know, that's something we need to talk about. So that is the rule. So if I go back to the rule page, if I go back to my derivative rules that I've got on the website for you, here's what it says. If you're going to do the derivative of arc sine of some stuff, that's a u in there. If you're going to do the derivative of arc sine of some stuff, it'll be 1 over the square root of 1 minus the stuff squared times the derivative of the stuff. So if we had arc sine of x squared, right? Arc sine of x squared. And we want the derivative. It would be 1 over the square root of 1 minus x squared squared, the x to the 4th, times 2x, right? The derivative of the x squared, derivative of the inside. The arc cosine rule is exactly the same, except it's got a -1 on the top. So that's nice, not much to remember there. And arc tangent, the last one we have, is very similar. There's no square root, and it's got a plus sign instead of a minus sign. So arc sine, arc cosine, arc tangent. That completes the derivative rules, okay, of functions we need to do. Your homework is section 3.4, which has, I think, you're going to have some of this trig, kind of inverse trig, some questions on some of those arc sine kind of things we talked about. It's also going to have a few derivatives for you to do. And then also do about 10 more on page 195. Okay? And then tomorrow's going to be all about, we'll go over some of that, and then tomorrow's going to be about practice and more practice on the derivative problems. Okay?